Welcome students to our lecture on transport number. What is transport number? It is a fraction of the total current carried by an ion. We all know that when the ions move, they carry with it certain amount of current. So the fraction of the total current carried by an ion, either cation or anion, is called transport number or transference number. It is given by the symbol T. T plus, it will be written as T plus for the positive ions and T minus for the negative ions. So the transport number is nothing but the current carried by an ion divided by the total electricity that is passed. If 6 Faradays of electricity is passed through the solution of an electrolyte AB, and if 2 Faradays are carried by A plus ion and the remaining 4 Faradays by B minus ion, then the transport number of A plus ions is given by current carried by this A plus ions, that is 2 Faradays, divided by the total electricity that is passed, is 0.332, sorry, 0.33. Now, the current carried by the B minus ions, written as T minus, is equal to 4 upon 6, where 4 is the current carried by the negative ions, which is equal to 0.66. If you add this 2, you should get equal to 1. But here I have not taken the third digit after the decimal point. That is why you may not get it exactly equal to 1. Now, quantity of electricity carried by each ion is directly proportional to the speed of the ions. Means, if the ions are moving faster, then they carry with it more amount of the current. So, a quantity of electricity carried by each ion depends upon the speed of the ions. It is proportional to the speed of the ions. Amount of electricity carried by anion is proportional to the speed of the anion. Amount of electricity carried by the anion, the negative ions, is proportional to the speed of those ions, negative ions. Amount of electricity carried by the cations, that is the positive ion, is proportional to the speed of the positive ions. So, with the definition that we have of transport number, T minus is equal to, if you go back, it is a current carried by an ion divided by total electricity passed. So here we have written, instead of the current carried, we are writing in terms of the speed, because here we have said electricity carried by the anion or the cation is directly proportional to the speed of the anion or the cation. So in place of the current carried, it is directly proportional to the speed of the ion. So the transport number of the negative ion is equal to speed of the negative ion divided by the total speed of the positive and the negative ion. Similarly, we can write the transport number of the positive ion is equal to speed of the positive ion divided by the total speed of the positive and the negative ion. If we add the above two equations, that is T plus T minus, we get it as equal to V minus upon V plus V minus plus V plus divided by V plus V minus. So we have just added the above two equations, and when we write, when we take the LCM, we know that the numerator, this will be equal to, what will be in the LCM will be V plus plus V minus, that is the common what is there in both the denominators. So this will be our LCM. In the numerator we will have V minus plus V plus. So what we have in the numerator is the same as what we have in the denominator, and it will cancel out and we get it as equal to 1. So we have transport number of the positive ion plus transport number of the negative ion is equal to 1. We need this formula later while doing our calculations. So sum of the transport number of the cation and anion is unity. So if you know one of them, suppose you know T plus, you know the value of T plus, say T plus is 0.3, then you can find out T minus. So how much will be T minus? T minus will be 1 minus T plus, rearranging this particular equation. So T minus will be equal to 1 minus T plus, which I can write as 1 minus 0.3, which is equal to 0.7. So using this formula, if one of the transport number is known, you can find out the other transport number of the other ion. Now, the method to determine the transport number. How are we going to determine this transport number? By using what is called as a moving boundary method. Now, in the moving boundary method, the transport number is directly observed as the rate at which the boundary between the two electrolyte solution passes down a tube under the influence of current. So here transport number is determined by direct observation of the rate at which the boundary between the two, so there is a boundary between two electrolytes and this boundary will be moving, and you can find out the transport number by directly measuring the movement of this boundary. So this is the apparatus that is used in this particular method. For the method to be accurate, it is necessary that the lower density solution must lie above the other to avoid mixing due to gravity. We take two electrolytes. You can see the two colors. So one electrolyte down here and the top electrolyte. So the electrolytes are selected in such a way that the lower density solution must lie above the other one having higher density in order to avoid mixing due to gravity. The two electrolytes must have common anion or cation. So one of the ion should be common. Here the two electrolytes that we have taken, one is HCl and the other one is cadmium chloride. So you have one is HCl here, the other one is cadmium chloride. And when you take this electrolytes like this, that is lower one at the bottom, having lower density on top and higher density at the bottom, and also the two electrolytes must have a common anion. Then there is a sharp boundary. Here you can see a sharp boundary between the two electrolytes before the start of the experiment. The apparatus consists of a long vertical glass tube which is graduated and fitted with two electrodes at the two ends. You have two electrodes at both the ends of this long glass tube, and we have two electrolytes. The electrodes are dipped in these two electrolytes. The tube is filled with a solution of cadmium chloride at the lower end and HCl at the upper end. A boundary is formed due to the difference in their refractive indices. Platinum cathode is dipped in HCl solution. So we have a platinum wire or platinum, this is your here, platinum cathode is dipped in HCl solution and is inserted at the top, and the anode, this is your anode, your cadmium, and this is your cathode. At the top, and the anode cadmium rod is introduced at the bottom. The tube is connected in series with an ammeter. We have an ammeter here to measure the current. We have the coulometer here, which measures the quantity of electricity that is passing, and a key. We have a key here and a battery. Okay. On passing electric current to the apparatus, H plus ions move to the cathode. So again, let me mark them. We have the cathode here, which is our platinum electrode. We have our anode here, cadmium anode, dipped in the cadmium chloride solution. So when electric current is passed through the apparatus, H plus ion moves towards the cathode. So here we have H plus ions and Cl minus ions. We have cadmium ions and chloride ions. Okay, cadmium will be Cb plus 2 and chloride is Cl minus 1. Similarly here we have H plus and Cl minus ions. Okay, so these ions move towards the respective electrode. H plus ions will move towards the cathode. Cadmium ions will also move towards the cathode. Chloride ions, that is Cl minus ions, will move towards the anode. Okay. Due to the migration of these ions, the boundary between the two solutions starts moving. It is seen to be moving. The initial and the final positions of the boundary, and hence the volume swept by the boundary, is determined. So initially we have the boundary here and final position. So you find out this particular distance from here to here. Okay, so this is the length of the tube. This is the length of the tube, which you have to find out by which the boundary has moved. If T plus of the cation, in general we have written A plus, is to be determined, you are finding the transport number. Now in our particular case we have two electrolytes, so we are finding out the transport number of the H plus ions and the Cl minus ions. The other electrolyte is a reference electrolyte. So here what we do is, if T plus of the cation A plus, so our A plus here is nothing but the H plus ion, is to be determined, then the electrolyte AX is to be taken in the upper part of the apparatus, and a layer of another electrolyte BX having the common anion is introduced in the lower part of the apparatus. Now the calculations here will be, let C be the original concentration. So you have the concentration of A plus ions in gram equivalents per ml of the solution. So you have C, which is your concentration. If the distance to which the boundary moves, if the length to which the boundary has moved is say L centimeter, then the area A square centimeter is the area of cross section of that particular tube. It has moved, suppose this much L, then it is a tube, isn't it? It's a glass tube. So if this distance is L, then the area of cross section of this tube is A square centimeter. Then the transport number T plus is given by this particular formula. Area of cross section into length into F, which is Faradays, which is 96,500 coulombs. C is the concentration divided by 1000 Q. Q is the quantity of the current which is passed, which is measured in the coulometer, and it is given by Q is equal to IT, where I is the current which is measured in amperes and the time in second. Many a times whenever problems are given, you have to keep a check that you have the proper units. Sometimes current is given in milliamperes, you have to convert it into amperes. Similarly, time may be given in minutes or any other units of time. It has to be in seconds, and this current has to be in amperes. In this problem, you can check in a moving boundary experiment with 0.1 gram equivalents per ml KCl solution using 0.065 normal lithium chloride as the indicator electrolyte, indicator solution, a constant current of 0.005893 amperes was passed for 2130 seconds. So you have to keep a check on this particular two units. They have to be in, this has to be in amperes, this has to be in seconds. In this particular problem, it is given to you in the proper units. The boundary was observed to move through 5.6 centimeter in a tube of 0.1142 square centimeter cross section. Calculate the transport number of K plus and Cl minus ions. So what you have to do is, you have to find out the transport number of T plus ions. Transport number is A, come on tell me girls, A into L into concentration into, come on tell me, let's go back if you have forgotten, ALFC. AL, what we missed here is F, that is the Faradays, 96,500, divided by this full thing divided by 1000 into Q, and Q is nothing but equal to IT. This is A, this is L, F, C divided by 1000 into I into T. So substitute all the values. A is equal to 0.00585893 into length. Length will be, sorry, the mistake. So eraser. Okay, cannot. Okay, so A is the area of cross section. Made a mistake. Area of cross section is here, length of the tube is here. Area of cross section 0.1142 into length of the tube is 5.6 into F is 96,500 coulombs into concentration is 0.1. Divide the full thing by 1000 into I. I is the current, that is in amperes, 0.005893 into time. It's 2130. Calculate this and find out the transport number of the H plus ions, and then you can find out the transport number of the negative ions using the formula T plus plus T minus is equal to 1. So you can rearrange this as T minus is equal to 1 minus T plus.